back again. We're going to try some titration calculations this time and see how these go. So I'm going to review a little bit the one we had looked at before and give a little bit more complete explanation this time. So let's pretend we go to a hardware store and we buy some hydrochloric acid sold as muriatic acid, and nowhere on the bottle does it tell us what the concentration is in terms of molarity. And maybe I want to use that in my lab, so I need to figure that out. Well, the way I'm going to do that is I'm going to titrate that hydrochloric acid with a known standard solution of sodium hydroxide. So for my problem here, let's say that it took 10.5 mils of my unknown concentrated acid to titrate 30 mils of 2 molar sodium hydroxide to its endpoint. I would, of course, be using bromethymol blue because I'm dealing with a strong acid, hydrochloric acid, and a strong base, sodium hydroxide. And I want to try to figure out what is the concentration of the acid. Now, from what I have so far, I can get a pretty good estimate of that number. Let's make sure we understand what was occurring, though. I've got my setup here with my ring stand, my double burette clamp, and I have here a burette. And then I'm going to add my base, 30 mils of sodium hydroxide base with a drop of bromethymol blue. Bromethymol blue indicator will be blue when it's basic. I'm then going to fill up my burette with hydrochloric acid that I got from the store. I don't know its concentration. I'm going to slowly add that by spinning the stopcock until I get the color change that I'm looking for. So I turn this, the acid drip, 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 drip into my Erlenmeyer flask, and it takes 10.5 mils so that what I end up with is my color changes from blue to yellow. As soon as it changes to yellow by the addition of 1 drop, I'm going to stop adding acid. At this point, we've reached the end point or the equivalence point. It's a theoretical point in which the moles of acid and moles of base should be equal to one another. Now, we know we've reached that endpoint because we got that rapid color change from blue to yellow as I added just a single drop of acid. Next, I'm going to use this equation, M1V1 equal M2V2. Molarity of the acid times volume of the acid equal molarity of the base times volume of the base. I may need to expand this and add one more variable as we move on, but for right now, we're going to try to keep it pretty simple. So when I say M1, I mean the molarity of the hydrogen ion, and V is the volume of the hydrogen ion of that acid. Molarity is of the hydroxide and the volume of the hydroxide. Now, why this matters is if my acid is HCl, 1 molar HCl will have 1 molar H+. But if my acid was, let's say, sulfuric acid, H2SO4, 1 molar sulfuric acid would be the equivalent of 2 molar hydrogen ion. And we'll address that here in just a bit. Now, I like to think through and predict my answers before I go on. If I'm thinking about it, it took 1/3 as much, basically, 1/3 as much HCl to be equivalent to, in other words, 3 times more base. So therefore, which is more concentrated, the acid or the base? I hope you said the acid must be more concentrated by a factor of about 3 times. So if the base is 2 molar, I'm going to predict my acid is going to be approximately 6 molar, or 3 times the concentration. So let's do the actual calculation. I'm trying to figure out the molarity of the acid. It took 10.5 mils of that acid to neutralize 30 mils of my 2 molar base. So this is pretty straightforward. 2 times 30 is 60 divided by 10.5 comes out to be the molarity is 5.7. That's the answer to the question, what is the molarity of the HCl? It's that simple. Now, the reason for this is HCl is monoprotic, so that if the HCl is 0.1 molar, the H plus is 0.1, and so is the Cl. If, though, we were to use a different acid, let's say sulfuric acid, if the sulfuric acid was 0.1 molar, the hydrogen ion is going to be the equivalent of 0.2 molar. Now, the real term is it's 0.2 normal, but for my class, I just go like 0.2 molar, and we just treat that in the problem as such. And of course, the sulfate is 0.1. So that if I were using 10.5 mils of, let's say, H2SO4, I wouldn't put for my molarity, the H plus, 0.1. Instead, I'd put 0.2 in there. That's how I teach it in my class. The alternative way to do this is to say molarity of the hydrogen ion times volume times N, where the molarity is still 0.1, but the N would be 2 for sulfuric acid because it donates 2 protons. So either use MVN or use MV, and understand that if you have a diprotic acid, you need to double the concentration. So let's kind of, and this is what I'm saying here. If you're doing sulfuric acid, 0.1 molar sulfuric acid is the equivalent to 0.2 normal of the hydrogen ion. If we were to use, let's say, aluminum hydroxide as our base, if the aluminum hydroxide was, let's say, 2 molar, what would be the equivalent hydroxide concentration? 6 would be correct because it's 3 times bigger based on the coefficients. 1 of these makes 3 of these. Very good. Let's try another problem. Let's pretend that we want to find, and I think this comes from your homework set, it's number 7, what is the pH of a solution made by dissolving 2.5 grams of sodium hydroxide in 400 mils of distilled water? Well, the first thing we need to do is figure out how many moles of base we have, because we know that molarity is moles over liters, and we need to know that in order to get the problem solved. So let's set this up. How many moles of sodium hydroxide is 2.5 grams of sodium hydroxide? Figuring out the molar mass, sodium weighs 23, oxygen 16, hydrogen 1, so that weighs 40 grams per mole. That's the molar mass of sodium hydroxide. Grams of sodium hydroxide cancel, like that, and I'm left with 0.0625 moles of sodium hydroxide. Now, those moles are going to be divided in 400 mils of water, so I'm going to calculate the molarity of my solution next. Molarity is moles of solute over liters of solution, and I have my moles of solute, 0.0625 moles, divided by my volume, 400 mils, is equivalent to 0.4 liters. That corresponds to a sodium hydroxide concentration of 0.15625 molar. Now, I need to figure out how that dissociates, because I'm not interested in the sodium hydroxide concentration, but the hydroxide concentration in order to get the pH. So the way this dissociates is into 1 sodium ion and 1 hydroxide. Now, if the sodium hydroxide is 0.15625 molar, based on the coefficients, the sodium also has that concentration, as does the hydrogen. So far, so good? All right, now's where it's going to get fun. We have a couple ways we could solve the problem. We know that POH is equal to opposite log of OH. Or we could do KW is H plus times OH minus. And I'm going to show you that both these steps will get us to the final answer in the same number of steps. If I know the hydroxide concentration, which is what I just determined, I can figure out the POH. It's equal to the opposite log of that number. Typing into my calculator, the POH is 0.8. Now that's not what the question asked. The question asked us, what is the pH? So that we'd have to take another step. POH plus pH is 14. So if I put my POH in as 0.8, then I get my answer. The pH is 13.2. And I'd ask you, is that a reasonable answer for this? And I hope you would agree it is, because we're adding a base in water. It needs to have a pH above 7. Now, if that makes sense and you want to solve the problem that way, by all means, that's a great way to solve it. If, though, you're wired a little bit differently, maybe you want to do it this way. The water dissociation constant is equal to the hydrogen ion concentration times the hydroxide. Now, we know the hydroxide concentration, and we know Kw is 1 times 10 to the negative 14th. So we can set up this equality, solve for the hydrogen ion concentration, and it comes out to be 6.4 times 10 to the negative 14th molar. From here, we're going to substitute in to go pH is equal to the opposite log of H+. We're going to put in for H+, 6.4 times 10 to the negative 14th. Type it in your calculator and guess what answer you'll get. If you said 13.2, you're right on. So I've shown you a couple different ways to solve that problem. This problem's a really nice problem. It helps you understand dissociation and molarity and some of the basics of pH calculations that we've been doing. So I hope that helped to see that one worked out. Let's try one more. This one says, what volume of half molar hydrochloric acid would be required to titrate 100 milliliters of 3 molar calcium hydroxide? Now, a few things that jump out to me is this is a titration question. We have an acid and we have a base. Now, I know the acid is monoprotic, it gives 1 proton, but the base gives 2 hydroxides. So even though it says 3 molar, in my mind, I'm going to think of this as a 6 molar solution when I'm solving my problem. I'm going to go ahead and write out an equation. Sometimes that helps to see what's going on. HCl plus COH2. This is going to be a double replacement and neutralization reaction. So the H and the calcium switch places, and what we end up with is water and calcium chloride. Now, in order to balance this, we have 2 OHs here. We're going to have to put a coefficient 2 here to make this a balanced equation, and a 2 here, and now it's balanced. So in other words, we need 2 parts HCl for every 1 part of calcium hydroxide to make this work. Now I'm going to put in some information. I'm trying to find the volume of the hydrochloric acid, and it's a half molar concentration. I know that I have 100 mils of the base, and it's 3 molar. Now, we could do this. Now, I'm going to tell you right up front, there's going to be a little problem, and we're going to fix it shortly. If we do M1V1 equal M2V2 and simply plug in our numbers, 0.5 times X equal 3 times 100, you'll get an answer of 600 mils of 0.5 molar HCl, which if it were a multiple choice test would be a choice, although it's not the right answer. Take a second and think about, where did we make a mistake? All right, if you're unsure, let me help you. Let's try this. Let's think about this. Molarity is moles over liters. So when we're looking at the HCl, moles of HCl is molarity times volume. We have 0.5 molar, 0.6 liters. You have 0.3 moles of HCl. If we play the same game with the calcium hydroxide, moles of calcium hydroxide equal molarity times volume, we get 3 molar times 0.1 liter, and we get 0.3 moles. So at this point, you're thinking, everything's great. We got the same number of moles. But what you need to pay attention to is, according to the coefficients of the balanced chemical equation, we need double the number of moles of HCl as calcium hydroxide, or half as much calcium hydroxide. So let's think about this. HCl, when it dissociates, goes to H plus Cl1 minus. COA, calcium hydroxide, goes into calcium 2 plus and 2 hydroxide. So if the HCl were 0.3 moles, the H plus would be 0.3 and the Cl 0.3. For the CaOH2, if it's 0.3 moles, the calcium's 0.3, it's the OH. It's not 0.3, is it? It's 0.6. Now, we said in titration, the moles of acid, that's the 0.3 moles here, have to equal the moles of base. And clearly, that's not the case the way we solved it. So what do we have to do? Well, it's very simple. What we're going to do is recognize that the 3 molar has the equivalent concentration of 6. We'd say 6 normality, in my class, 6 molar. And now when we solve it, we'll get the right answer. So look at this. M1V1 equal M2V2. 0.5 times X equal the equivalent of 6 molar hydroxide times 100 mils. And now we have the correct answer, 1,200 mils of 0.5 molar HCl. I know I'm going a little faster these, but through the beauty of your computer, you can slow me down. You can watch me over and over again until you get this stuff figured out. Okay? I'm going to skip this last example. I'll leave it up on the screen. In my class, my students are supposed to figure out the percent acetic acid in vinegar with some titrations. If we meet in class, we'll go through this. Otherwise, there'll be no questions similar to this on your test. All right, I'll stop there. I hope this was of some help to you, and I wish you good studies of chemistry. Take care and stay healthy. Bye-bye.